Hey guys, today we're going to look at the distance from a point to a line, and this works, well, we will do both in R2 as well as in R3. Okay, so the line we're going to look at, we're going to use the equation, so the line will be AX, we're going to use Cartesian form here, plus BY plus C equals 0. So this is in R2. The normal to this line then would be given by, which we'll call it N, like that, which is going to be AB. Okay? So, a generic point on XY, so that's going to be, we'll call that, whoops, let me do it like this. So we'll call it point 1, and it's just going to be X1, Y1. Okay, and then we'll have a specific point, okay, which we will write as P0, X0, Y0. And this is going to seem a little complicated, a little convoluted, and it kind of is, but when I show you the formula, it actually just works out pretty easily. Okay, so I'm just actually going to jump ahead to what the formula is here for brevity's sake. So I'm going to give you two versions, okay? So the first is going to be that D is equal to, and we're going to take the absolute value of the vector PO to P1, and then we take the dot product of that with the normal, and we divide it by the magnitude of the normal. Okay, so that's our first one, and sometimes that's the easier one to use. I find most of the time the other one is a little bit easier to use, and so that's when I do the example, I'm going to use it. But it's just going to be A times X1. Now you'll notice X1, so that's the specific point. And then we've got B Y1 plus C, and we take that and we divide it by the square root of A squared plus B squared. Okay, and so this is actually, this is the same formula, it's just another way of writing it, and so arguably a little easier to get your head around, but it will give you the same answer regardless how you do it. So we're going to do this example here, and so I'll start by writing out that formula, and like I said, I'm going to use the second formula. It'll work the exact same if you use the first formula. It doesn't make a difference, okay? Even the steps will actually look the same because you're doing the same thing. It's just another way of writing it, okay? So I'm going to do that, and then I'm going to divide by square root of A squared plus B squared. So then I'm just going to start subbing in the numbers, okay? So I'm going to have negative 2 times 3, because A is negative 2, X1's 3, and then B is equal to 3, and Y1 is equal to negative 1, plus 6 for C, okay, and then we divide by the square root of negative 2 squared plus 3 squared. Okay, and so that works out to 3 over root 13. And you could rationalize that, but I'm not going to bother for our purposes. Okay? And I wouldn't necessarily expect you to. So there we go. So that's not that bad, eh? So I know what you're thinking. You're thinking, let's do it in 3 dimensions. That would be way more exciting. So this time I'm going to use the vector form here. So for the equation, just because it's a little easier when we're dealing in 3 dimensions to use the vector form, I'm going to say that it is R equals, and we've got that specific point, and then plus T U, that's a direction vector, and that's where T is an element of the real numbers. Okay. And there we go. Okay, so let's see. A specific point on this line is, we'll call it P0 again, and that's X, Y, Z, 0, 0, 0. And there we go. So there's our specific point. Okay. Let's see. So The distance from a point P1 to the line L can be found using the formula. And so again, I'm going to give you two versions here. So am I going to give you two versions here? Yeah, I am. So no, I'm just going to give you one. We're going to use D is equal to the absolute value of, and what we do is we take the vector that goes from the specific point that's given to the point we're measuring from, and we're going to take the cross product of that with the direction vector, okay? And you're going to take the magnitude of that, and then we're going to divide it by the magnitude of the direction vector, okay? And that'll give us the distance. All right, so example. Let's take a look at this one. So first of all, we have to find this vector here, the P0 to P1 vector, okay? And so you're just going to do subtraction because, of course, we've got this guy. That's our 1 point. There's P1, and then P2 or P0 rather is right there, okay? So doing subtraction with those is going to give us 1, 1, and -3. Okay, and that is a vector. Okay, so there's that. So the next thing we have to do is we have to find what is the cross product with that vector and the u vector. Now our u vector, of course, is found right here. Okay? So, cross product, and that's going to give us 6, 3, 3. Okay? So now, all I have to do is I use my formula. I say D is equal to, and it's the P0 to P1, whoops, that's an R, P1, crossed with the direction vector, and then divided by the magnitude of the direction vector, okay? So we already have, we got this guy right here, okay? So that's going to be square root of 36. And I am skipping some steps here, so I hope that's okay. But we got 36 plus 9 plus 9. Okay, so I'm just taking the square. I'm squaring each of these right here, right? Squared, squared, squared. Add them up, square root it, and that's going to find the magnitude of that. And then I'm going to divide by the magnitude of the u vector, which is going to be square root of 1 plus 4 plus 0. I'm just going to write plus 4. I'm not going to write plus 0. Okay, and then we'll just pick it up over here. And we get the square root of 54 over 5. And there you go. And that's it. Okay, so this is, the formulas look a little intimidating, but they're actually fairly simple if you just go one step at a time. Okay? So let's make it a little bit more challenging. Let's look at the distance between two parallel lines. So to find the distance between two parallel lines, what we're going to do is we're going to find a specific point on one of these lines. So let's write that. So we're going to, step 1, we're going to find a specific point on one of these lines. Find a specific point on one of these lines. Okay, and then we're going to find the distance from that point to the other line, because of course they're parallel, so the distance is the same regardless of which point we use on the first line. Okay, so find the distance from that point to the other line. There we go. Okay? And you can use that same distance formula that we had before. All right? So I am going to let you try that example yourself because it's the exact same as the first example we did once you find that point. So the only thing new is finding a point. But of course you can just let x equals 0 and solve for y on one of the points, and that's probably going to be your easiest or your best bet. Okay, so let's look at perpendicular line from a point to a line. Okay, so we get a little picture of what I mean here. So perpendicular. So okay, so the line. Well, let's go through this. So we're letting this line. Okay, we're in 3 dimensions here. Be defined, or be a line defined by its vector equation, and we've got a point, a generic point in R3. Okay, the line perpendicular to the line L that passes through the point is what we will call a perpendicular line, which is not that surprising. So perpendicular line. That says line. There we go. And it intersects the line L at a point called, at a point F, we'll call it. And we call this the foot. Okay? The foot of the perpendicular line. Okay? So you can see here my thing here. I got the point there. Okay? So it's going down to this line that it's perpendicular with. Okay? And that point where it meets is the foot. Okay? The foot, which of the perpendicular line, may be found from the equation, and it's just PF. Whoops, PF. So we take the vector from P to F, and then the dot product with the direction vector of the other line is equal to 0. Okay. So the vector equation would be R OP, okay, where O is the origin, plus SPF. Okay, and that's where S is an element of the real numbers. Okay, so it's a little bit more confusing than what we were doing before, so I'm going to walk you through an example here. Okay, so we're going to find the foot of the perpendicular line from the point to the line L. Okay, let's see. So the first thing we're going to do is we're going to say, well, what's P? Okay, P is equal to, then obviously it's this guy right here, right? Nope. Where is it? Oh, there it is. It's right over there. 3, -4, 2. I guess I always point to the screen, and I realize that you guys can't actually see what I'm pointing to. So, whoops. But anyway, so there's P. Okay, we've got U, our unit vector. I'm gonna zoom in because I'm taking up too much space here. U is that's our 1, -3, 2. Okay, and so F is going to be -2 plus T, and then we've got 3 minus 3T, and then we've got 1 plus 2T. Okay, so PF, our PF vector, is then going to be -5 plus T, 7 minus 3T, and -1 plus 2T. Okay? And since I know that PF and the dot product with the U is equal to 0, what I can do then is I can say, well, then all this stuff here, okay, is going to have to equal 0. Okay? Or when I take the dot product, that is. So the formula, or the equation you end up with, is we end up -5 plus T, okay, minus 3 times 7 minus 3t. And I'm just taking the dot product of the u and the pf. They look complicated because there's so much in there, but you know, we're just breaking it into the components. Okay. So sorry, just to recap, because I realized that was not clear at all. So these are the parts. That's the x part of pf. I'm multiplying it by the x part of u, which was 1, so I didn't multiply it by anything. Okay, but then I had the y part. Whoops, I meant to use a fancy color. We had the y part of pf multiplied by the y part of u. Okay, and then the y part of z and the y part of u. Okay, so that's where that's coming. And then I'm just adding them all up because it's the dot product, and then it does equal 0. Okay, so I just go through, I collect like terms, and what I get is that t equals 2. Okay, so, and I'm running out of room because I wrote way too big here, but so that means that f is going to be, and I had f in terms of t, so I can just sub in that t equals 2 for the f, and I get that f is equal to 0, -3, and 5. Okay, and that's that. All right. So let's see. So find the equation of the perpendicular line from point P to the line L. Okay, so if we're finding the equation, well, first of all, I can use my point. I just found F, right? So I can use F as my point. Let's see. And then I just need, show you, or you can use P alternatively. I'm actually going to use P. Okay. So anyway, so you need your P. You need your direction vector. You need your point. Okay. So my point, I'm going to use. I'm just going to use the P value. You could use the F value. It doesn't make a difference. And then the vector is just going to be PF, because we know those are both points on the line. So PF is going to equal -3, 1, 3. Okay, so there's our vector. So that means that I can just say R is equal to, and I'll have my point, which I'll use 3, -4, 2. Like I said, you could use F. The reason I use P is I'm kind of in the habit of using, if the point's given in the question and then there's another one that I solved for, I'm probably going to use the one that's in the question because I know it's right. Actually, I should use S because I already used T. It doesn't really matter. And then we've got -3, 1, 3 as our direction vector. And that is where S is an element of the real numbers. So there you go. Okay, so the last part is find the distance from the point P to the line L. Well, that's just going to be using the distance from P to F. So this is actually, because we already found F, you don't even have to do anything super fancy here. We can just say, well, D is the magnitude of P to F. Okay. So it's going to be the square root of 9 plus 1 plus 9. And it just equals root 19. Okay, and that's it. So that's all we have for today. So until next time, go Sabres.